Just a little over 3 years ago, I was at our Premier Business Leadership Series in Singapore. And the head of the risk department from UOB Bank told me that they had implemented our SAS risk management, but it was taking 18 hours to be able to compute the value at risk. And he asked me, is there anything you can do to make this run faster? So when I got back to Cary, I spoke to our risk people to try to understand exactly what they were computing. And it turns out that what they were actually doing is computing a covariance matrix of risk factors. They'll have, 3,000 or 4,000 risk factors over a 2 or 3 year period that they've collected. And we use that to build a covariance matrix. And then we convert that covariance matrix, as sort of a statistical thing, into a Koleski decomposition. Then we multiply that by a set of random numbers over and over and over again. And each time we do that, we generate a possible market state of risk factors. And then we generate another possible market state. So we go into this simulation mode where we keep generating 100,000 different possible market states, sometimes 200,000. So now we've got a whole universe now of possible market states. And we then begin to price the entire portfolio using pricing functions. And once we've got every portfolio priced, then we can look at the distribution over those 100,000 different market states and determine the distribution of risk. We simply take the 95th percentile, and that's the value at risk. So it's a very simple computation, but it's a huge, massive amount of data, of actually computations that have to be done. For the UOB Bank example, I estimated that it would be about 200 trillion operations that had to be performed. Now, 3 years ago, our processors were only executing 2 billion instructions a second. So there is absolutely no way we can do 200 trillion operations any faster unless we start to use more processors. And that's what we came up with. I worked with our advanced computing laboratory, and they began working on this problem, spread it over hundreds of processors using some very inexpensive blade computers. And that allowed us then to take this 18-hour job down to 15 minutes, almost to the point where you can make real-time risk decisions about your portfolio. So let me show you a little bit about this blade technology. I want to talk about a blade, and this is a blade that you see coming out here. We've taken the top off, and you see inside you've got these two big gray things that look like a Chevrolet symbol. Those things are radiators. They're there just to dissipate the heat from the chips underneath. And here's what's underneath. Let me show you that. These are chips that are made by Intel. They're called Sandy Bridge. And here's an actual size of that chip right here. So it's pretty small, but it's about an equivalent of a 100-watt light bulb, so it gets very hot. And those big radiators help dissipate the heat from these chips. Now these chips are not just one computer, but each chip has 8 cores. You think of a core as a complete computer except for memory and disk. So each core basically represents one computer, and there's 8 of them on each chip, and there's 2 chips inside each blade. So it turns out, though, that not only do we have the 8 cores, but they have created something called hyper-threading, which allows us to run 2 threads or 2 processes on each of these cores. So that means that on this single computer, this single blade, we can run 32 processes, and each process can execute over 3 billion instructions per second. So this one box, we can run 96 processes in parallel, and if we want to run more, we have to add more blades. Let's continue exploring here. These are memory sticks, and each memory stick contains a number of DIMMs. These are 64-bit memory chips. And we recommend, as a starter, we like to have at least 4 gigabytes per process. So we're recommending purchasing 128 gigabytes of memory. And it's interesting, you can actually go up to 256 or 384, and this fall we're going to see 32 gigabit DIMMs that will actually allow us to put 768 gigabytes of memory in one of these blades. So the amount of memory that's going to be available is going to be enormous that we can purchase. Well, let's put the memory back. So now we've got the cores. Now they've got the memory, and now we have some disk. That makes a complete computer out of every one of these cores. And the memory is 600 gigabytes for each one of these 2 disk units. And what we like to do, we'll just put this back in its rack. A rack has quite a few blades in it. Let's first of all build a chassis. A chassis has got 16 blades in it. It's called a chassis. And you can actually stack 3 chassis on top of each other into a rack. So this is a rack. And we call these blades because the blades fit into the rack like a knife blade. They also make boxes that look almost exactly the same, except they're flat and they lay sideways. But the inside looks very, very similar, except there's more disk space. But this new Sandy Bridge processors that we're recommending now for high performance, 1,536 processes we can run on this one box. It has 6.1 terabytes of memory, 57 terabytes of disk. So it's an enormous, complex. This rack of blades is about that wide. It's about like a refrigerator. It's about this tall and about that like that. So it's very compact, and we can get 48 blades in one of these racks. So, and if you want to think about, well, how do you conceptualize this? And I like to think of it as one big computer. It's got all these processes that we can use. It's got all this memory that we can use. And let's take an example. If you have, let's say you have 1.5 billion records. 1.5 billion records. Well, if you've got 1,500 processes, you could simply give each process about 1 million records. So if every one of these processes owns 1 million records, and I want to find out, for example, what is the sum of revenue? Well, then I will have a central controller up at the very top here that asks that question of everybody. Would everybody give me the sum of revenue? So this blade figures it out, and that blade figures out theirs. Everybody figures out what the sum of revenue for their data, and then these are binarily added together until we get the answer. And it will take less than a second. So we can process 1.5 billion records to compute a sum of revenue in less than a second. Now, most of our analytical computations are much more complex than a simple sum. Building matrices, inverting matrices, doing iterative analysis to be able to work on nonlinear models. But these are especially good if they're in memory, because for nonlinear models, we have to estimate get an initial estimate of the parameters. We have to go through the data to get a second estimate, and we just keep having to re-estimate the parameters until we're finished. We may go through 15, 20 times that we have to go through all of that data. The fact that it's all in memory makes it much, much simpler, much faster. We don't have to keep reading the data in all the time. So that'll give you some idea of the box that we're working on. You know, we can start with as few as eight blades, or 16 blades, or 32. It depends how much data you have. That's what the decision point is. Now, I'd like Oliver Schaumenberger to come up. Oliver is our head architect for high performance, and he will show you some of our high performance procedures in action, and you'll be amazed at how fast they actually run. Oliver?